We've learned to write the products of precipitation reactions. Another kind of reactivity we'll be able to master is acid-base reactions. Before we get into reacting acids with bases, let's go back and define some terms from your high school class. Now, what defines an acid or a base, it depends on which part of history you're looking from. Originally, there was an operational definition of acids and bases. For example, acids were sour and they conducted electrical current. Bases were bitter. They also conduct an electrical current. So the operational definition is based on how they operated. You can imagine that that's pretty limiting, and certainly we don't want to be tasting everything to see what its properties are. It is interesting though, for food that tastes sour, you can bet there's an acid in it, and bitter food, it's basic. That's kind of interesting. Humans have an aversion to bitter foods, and a lot of the basic compounds are poisonous to humans. So gotta love that evolution kind of thing. The next definition of acids and bases that came along was the Arrhenius definition. Right? The Arrhenius definition, named after Svante Arrhenius, and he described what acids and bases do in aqueous solution. Acids dissolve in water to produce, hydronium. H3O plus. And we had a little discussion about that. You may have seen more simply that acids produce H plus in water, but really when I stick an H plus onto a water molecule, I get hydronium, H3O plus. Now we've learned to recognize some acids already. You had a list of 6 strong acids to memorize. I hope you could tell me one right now. My favorite is HCl. It's nice and cheap. That was a strong acid, and I knew it was strong because I memorized it. I'm so sorry. I hate memorizing, but you got to start somewhere. I hope you also have a favorite weak acid. If you don't already, you better learn that my favorite weak acid is acetic acid. Acids produce hydronium. Bases produce hydroxide. So acid dissolves in water to produce hydronium. A base dissolves in water to produce hydronium. You may well have a favorite strong base. Mine is sodium hydroxide. But any ionic compound that contains hydroxide and is soluble in water will be a strong base. I hope you have a favorite weak base. My favorite weak base that I hope you recognize is ammonia. So those Arrhenius definitions are certainly more precise than the operational definitions were, but this limits us to aqueous solutions. So let's see if we can come up with a broader definition for acids and bases. From now on, if I don't tell you which definition I'm talking about, I mean the Bronsted-Lowry definition. And there are pictures of Bronsted and Lowry. They defined acids and bases by the nature of the chemical change they undergo. They said that an acid was a proton donor and a base was a proton acceptor. And when they say proton, they mean H+. I remember finding that confusing at first because a proton is just a subatomic particle. But the hydrogen atom has atomic number 1. That means it has 1 proton in the nucleus, and in a neutral atom, it has 1 electron. If you make the H+ ion by removing that electron, all that's left is the naked little proton. So, proton, H+, those are synonymous. Now let's see if we can write an equation for what happens when my favorite strong acid, HCl, dissolves in water, so that we can see indeed that it is a proton donor. HCl in water being a strong acid. How do I know? I memorized it. I'm so sorry. It's strong, so I'm going to show the reaction going to completion with a forward arrow only. And it's a proton donor, so it's going to lose H+, leaving me with chloride minus and hydronium. I've written this equation for you before, and I've told you again why I like to see the water explicitly. I like to see the acid give its proton to something. And in this case, the water is acting as a base. It is the proton acceptor. A base is a proton acceptor. And I want to see if you can write the equation for what happens when my favorite weak base dissolves in water. Go ahead, pause the video. All right, I recognize that ammonia is a weak base, I'm afraid for now because of authoritative knowledge. But if I know that, that tells me what happens when I put it in water. Because it's a base, it's a proton acceptor. It picks up H+ to become ammonium. And if it's the base, water must be acting as an acid. It's picking up the protons. It's donating the proton and leaving us with hydroxide ion. One last thing for this equation. Ammonia is a weak base, so this is really an equilibrium. There will be mostly ammonia left over in the solution of ammonia, very few ions present. So a couple things about that. One is that each more sophisticated definition includes the lower level definition. The Bronsted-Lowry definition means that I get hydronium when I put the acid in water. An Arrhenius acid is a Bronsted-Lowry acid and vice versa. And similarly, an Arrhenius base is also a Bronsted-Lowry base. We made hydroxide ions in solution. Interesting thing about the water, in the first equation it acted as a base, and in the second reaction it acted as an acid. I suspect if you went up to a person on the street, water would be considered neutral and neither an acid nor a base. But people who think that water is neutral are using the Arrhenius definition. When you put water in water, you don't get much happening. With the Bronsted-Lowry definition, though, the function of water depends what you put it with. It can react as a base or it can react with an acid. It depends what it's reacting with. One other thing about acids while I'm here. Everything that has that is an acid contains a proton, but not everything with a proton is a good acid. You might think acid-base chemistry is really simple, and we're taking it in simple little chunks. But to be able to recognize acids from their formulas is really a pretty high-level skill. We'll come back to it again in Chem 125 in the winter, and then at an even deeper level in organic chemistry in second year. But don't worry, I'm not going to get ahead of you. Trust me, I know what you know right now. So once we recognize an acid and a base, we can recognize that an acid-base reaction is just a proton transfer reaction. And that makes it so easy to predict the products of the reaction. I just move the H+ from the acid to the base. One more piece of jargon to take care of while we're generally talking about acids and bases. I want to introduce you to the concept of polyprotic acids. And you scholars of language know that poly means many. So a polyprotic acid has more than one proton, more than one hydrogen. And a good example is, you know what this molecule is called, right? That's sulfuric acid. It is diprotic. It has 2 H+ it can lose. So let's see if we can write equations showing what happens when we put sulfuric acid in water. When you memorized the 6 strong acids, you saw that the first ionization of sulfuric acid was strong. So we're going to have this reaction go to completion. Now you can predict the products by knowing that all that happens in an acid-base reaction is that the proton transfers from the acid to the base. Go ahead, pause the video. So the acid loses one H+, one at a time, friends. And the base, in this case the water, picks it up to make hydronium. I showed you 2 styles of equations before with acids, one using hydronium and one using H+. But now that I've told you that acid-base reactions are easy to remember because protons transfer from the acid to the base, I like to show the base explicitly so I can see where the proton went from the acid to the base. All right, now the product of that reaction has another hydrogen in it. So we can show another step showing the hydrogen sulfate ion reacting with a proton reacting with water, to lose another proton. Now when you memorize your strong acids, only the first ionization was strong. Hydrogen sulfate is a weak acid, which means that this reaction will be an equilibrium. Only some of the hydrogen sulfate ions will lose their protons to make sulfate ion. So that's the difference between weak and strong. It's kind of authoritative knowledge that the first ionization goes to completion and the second one doesn't, but I can justify that as a trend. What happens when you have something act as an acid, you remove an H+ from a remainder that is negatively charged. Now, all of chemistry boils down to opposite charges attract. When I try to pull a positive away from a negative, there's an attraction I have to overcome. When I get down to the second ionization, I'm trying to remove an H+ from something that's got a -2 charge, so the attraction is even greater. It gets harder and harder to remove the proton as the anion becomes more and more negative. So that makes sense to me that the second ionization is weaker than the first one. All right, friends. Let's move on. Now that we know what happens when we put acids and bases in water, let's mix them together and see what happens. And just as before with the precipitation reactions, I think the key to happiness is being able to visualize what's in the flask. So for this reaction, I'm going to do in considerable detail this first time. I'm going to draw a picture of what's in the flask. I see one of my reagents here, and I hope you know that that formula represents what compound? Nitric acid. So I'm going to ask myself, what happens when nitric acid dissolves in water? This goes way back to our unit on electrolytes. The first question I ask myself is it ionic or is it covalent? I don't see any metals there, only nonmetals. So this is a covalent compound, and usually covalent molecular compounds don't dissociate. But this is an exception. I memorized that this is a strong acid. And what do strong acids do? They react completely with water to make hydronium ions and nitrate ions. That's what's really swimming around in the flask. Now, if you wanted to reassure yourself by writing off in the corner somewhere that that nitric acid plus water gives nitrate ions and hydronium ions, you could do that to reassure yourself. That's where I get the hydronium and the nitrate from. All right, what's in my other beaker? I've got some potassium hydroxide, and the question I'm going to ask myself first, is it ionic or is it covalent? I see metal and nonmetal, that's ionic. And it also aqueous, it's dissolved in water. When I dissolve an ionic compound in water, I get the ions. So that's what's in my 2 reagent bottles. Now I'm going to mix them. And for the split second before the reaction can happen, I've got hydronium ions and nitrate ions and potassium ions and hydroxide ions. So what's going to happen in the reaction? Now you'll remember this story from when I introduced the first precipitation reaction. I said that positive and negative ions have to go together. And we're not going to consider the old combinations, H plus with nitrate, because we know that went completely to the ions. Similarly, we know that potassium and hydroxide are soluble in water. So we're going to try the new combinations. I'm going to try the hydronium with the hydroxide and the potassium with the nitrate. And just for fun, when I write the equation, I'm going to start with the net ionic equation this time. Net ionic equation isn't much of a shortcut if I have to write the molecular and complete ionic equations first to figure what it is. When I see the lovely picture of the flask, I'm going to be able to see the net ionic equation right away. For the combination of potassium and nitrate, if you go look in your table of solubility rules, you will see that ionic compounds containing potassium ions are soluble. They're not going to react. They're just going to keep swimming around. So the potassium's a spectator ion and the nitrate's a spectator ion. Now let's see what happens when I put hydronium with hydroxide. I recognize that hydronium indicates an acidic solution and hydroxide is the species that shows a basic solution. So this is an acid-base reaction. And all that happens in an acid-base reaction is that the proton, the H+, transfers from the acid to the base. If I lose an H+ from H3O+, I am left with water. Now that H+ gets transferred to the hydroxide. H+ plus OH minus makes another water. Ta-da! All I need now is the state. We're being complete. You know what water is. It's a liquid. So there's the net ionic equation I see when that strong acid reacts with that strong base. All right, now I've shown you the net ionic equation, but now that I've shown you the shortcut, let's make sure we can write all 3 kinds of equations on the next slide. We started with nitric acid and potassium hydroxide. And this time I'm trying to write the molecular equation. It turns out that just like precipitation reactions, at the level of the molecular equation, acid-base reactions are also exchange reactions. There's my abbreviation for reaction, RXN, which means we take the positive of one and combine it with the negative of the other. H+ and OH- makes water. Now we're going to take the positive of one and the negative of the other, and that makes potassium nitrate. Now, I didn't show you a video of this reaction because it's really boring looking. You don't see any changes. But that would help you to decide the states. You don't see any precipitate, so that potassium nitrate must be aqueous. If I didn't have the observation in front of me, I would rely on the table of solubility rules. And don't forget, you don't memorize that. I'm going to provide it to you anytime you need it. The water state, you know, that's a liquid. So there we are. At the level of a molecular equation, an acid-base reaction is just an exchange reaction. All right, next we're going to write the complete ionic equation showing everything as it's swimming around in the flask. So I'm going to write here the species that I showed you in the beakers before. Remember, we said that if you have nitric acid, which you recognize as a strong acid, that reacts with water to make hydronium ions and nitrate ions in solution. Then we looked at the potassium hydroxide. We said that was ionic and soluble, so I get ions in solution. Now, translating the products, I look at water. And again, the question I always ask myself is it ionic or is it covalent? Only nonmetals. It's covalent. It's molecular. Don't you dare break those bonds. Covalent compounds stay as molecules in solution unless they happen to be acids or bases. Last translation, potassium nitrate, ionic and dissolved in water. That gives me ions in solution. Now, about balancing these equations, I should have paused and made sure the first equation was balanced. It was. You may notice that this complete ionic equation is not balanced now. And here's what happened. I pulled a fast one on you. To take it from nitric acid to hydronium plus nitrate, I had to add a water molecule. You can look at the equation I wrote at the top of the previous slide. So that means to keep it balanced, I had to also add a water to the product side, and that means I'll end up with 2 waters now. And if you're a skeptic, go ahead and check. That is indeed balanced now. All right, net ionic equation. You don't need me to teach you this. To go from a complete ionic equation of any type to a net ionic equation of any type, you just leave out the spectator ions. Go ahead. Pause the video. All right, the nitrate and the potassium ions are exactly the same on the reactant and product side. I'm left with hydronium plus hydroxide. Gives me 2 water molecules, which is exactly what we saw when we looked at the beakers. Woohoo! Now, at the level of the net ionic equation, I love net ionic equations that cut out all the clutter. At the net ionic equation level, I can see that an acid-base reaction is just a proton transfer. Those darn old molecular equations tell me what bottles to take off the shelf, but they make it look too complicated. They look like more than a proton transfer. But at the net ionic equation level, acid-base reactions are proton transfers. Ready for another one? So this time, I'm going to combine some acetic acid with some sodium hydroxide. And once I give you a couple of hints, I'm going to let you write that molecular equation. We need to know what general type of reaction this is to know how to treat it. You have to be able to recognize acetic acid as an acid and sodium hydroxide as a base to know that this is an acid-base reaction. And once you know that this is an acid-base reaction, you know at the level of a molecular equation, it's just an exchange reaction. The positive of one goes with the negative of the other. Go ahead, pause the video. All right, I'm going to take the positive H plus from the acetic acid and the negative hydroxide from the sodium hydroxide, and I'll make water, which I know is a liquid. Then I'm going to take the positive of one and the negative of the other, and I'm going to make sodium acetate. You've eaten sodium acetate before, probably. That's the ionic compound they sprinkle on your salt and vinegar chips to give you the flavor of vinegar without making your chips soggy. Now, what state is the sodium acetate? You could look at a table of solubility rules. I hope you will. I'm afraid I've been looking at it so long that I know that sodium salts are always soluble. So there's aqueous. Are we balanced? Yes. And what I love about the way I put circles and squares on that is that you can see where every piece of it went. That is so much better. Probably when you started balancing equations, it was just atoms dancing everywhere. But now you're starting to see that the atoms actually go somewhere. And if you follow them one side to the other, you can simplify your balancing. All right, next one, complete ionic equation. And wait, I'm going to get you started on this one. In the previous example, we had a strong acid. Here we've got a weak acid. And I'm going to remind you of what we saw when we looked at the unit on electrolytes. Weak acids are less than 100% ionized in water, less than 100% dissociated. And as a matter of fact, in a solution of acetic acid, most of it stays as the intact molecule. Very little of it breaks into ions. So I'm not going to show that complication. What most of it is doing is staying as the molecule, so I'm leaving the intact molecule there. That's, remember, because it's a weak acid. All right, I got you started with your first weak acid. Now you can pause the video and finish the complete ionic equation. All right, we're going to translate the molecular equation. Sodium hydroxide, metal and non-metal. That gives me ions in solution. Now on the product side, water, ionic or covalent? That's all nonmetals, that's covalent. Don't you dare break a covalent bond. Molecules stay intact when you put them in water. And finally, sodium acetate, that's metal and nonmetal, that's ionic. Now, I don't care if you don't know that that's called an acetate. That's not one of the ions I gave you on your list to memorize. I just care that you know what to do with the formulas there. So there we go, a complete ionic equation representing everything that's swimming around in the flask. Finally, a net ionic equation. Go ahead, pause the video. Now, some of you may be worried, well, wait a minute, I've never done a net ionic equation with a weak acid before. You don't care. What happens when I go from a complete ionic equation to a net ionic equation is that I leave the spectator ions out. And this time there's only one spectator ion. There's only one thing that's exactly the same on the reactant side and the product side. So I've only got one spectator ion. That's okay. I'll just leave it out when I write the final net ionic equation. Acetic acid plus hydroxide gives water, that's a hydrogen there, plus acetate ion. Woohoo! And now, again, that beautiful thing, at the level of the net ionic equation, you can see that all that happens in an acid-base reaction is that the proton transfers from the acid to the base. Now, some of you are thinking, wait a minute, in high school, they told me that when I get an acid-base reaction at the net ionic equation level, it's hydronium plus hydroxide. Did they tell you that in high school? That's only true when you react a strong acid with a strong base. Maybe that's all you saw in high school. One last thought about this example. Because the acetic acid is a weak acid, you might have worried that I should have shown reversing equilibrium arrows for each one of these equations. And certainly that wouldn't be wrong, because in truth, every reaction is an equilibrium. But when the equilibrium lies heavily to the product side, when it goes essentially to completion, I like to just show the forward arrows. That makes my life so simple. Here's the guideline I'm using. If either one of my components is strong, and sodium hydroxide is a strong base, if either one of my components is strong, I'm going to say that the reaction goes to completion. Which equation is the right one? They all are. And the one I write depends on the context that I'm in. The one you write is the one I ask you for. One last example. Let's take some iron 3 hydroxide. And if I did this for you, I would put some solid at the bottom of the beaker. If you check the solubility rules, you will see that iron 3 hydroxide is not soluble in water. So I've got a solid there. And I'm going to react it with hydrochloric acid. We're going to write all 3 equations. And I'm not going to stop again and again to tell you to pause the video. I'll just encourage you to try to get ahead of me as much as you can. So anytime you're feeling inspired, you go ahead spontaneously and pause the video. Here I go. First of all, I have to recognize what kind of reaction I've got. I've got an ionic compound with hydroxide in it. That's a base. I've got hydrochloric acid. You memorize that as your favorite strong acid. It's an acid-base reaction. And at the level of a molecular equation, this is just going to be an exchange reaction. The positive of one goes with the negative of the other. All right, the positive H plus from the acid goes with the negative hydroxide from the base and makes water. Wait, you say, there are 3 hydroxides. Oh, well that means I'll need 3 H pluses. And that will make me 3 waters. See if you can see where the atoms are going. It's so much easier to balance the equations. Now, the other product, positive of one, iron 3 plus, negative of the other, chloride minus. I will need 3 chloride minuses to balance the charge on the iron 3 plus. And look, we're already balanced automatically because we paid attention to where the atoms were going. Now I'm going to find the states. You know water, that's a liquid. And if I looked in my table of solubility rules, you would find that chloride ions, the compounds with chloride ions are soluble. There are some exceptions, but iron 3 plus isn't one of them. So the state of that would be aqueous. All right, next, complete ionic equation. I'm going to translate the molecular equation one formula at a time to show what's really swimming around in the flask. So here I go. Iron 3 hydroxide, it's ionic. But wait, don't you dare break it into ions because it's a solid, it's not dissolved in water. Solids we've seen as products before, and we left them together. But I don't care if the solid is a reactant or a product. I'm going to treat it the same way when I try to decide what's actually in the solution. All right, next, HCl. 2 nonmetals, covalent. So normally I would think that would hold together, but wait, we're on our guard for acids and bases. You memorized that HCl was a strong acid, so you know that that produced hydronium plus chloride ions when I put it in water. Hey, wait, there were 3 of those. So I'll get 3 hydroniums and 3 chlorides when I add 3 water molecules to it. If my first equation was balanced and I keep track as I go, I'm going to stay balanced. All right, next we're going to translate the products. Water, only nonmetals, covalent, leave it together. And finally, iron 3 chloride is a metal and nonmetal. That's ionic and it's dissolved. So I get iron 3 plus ions and 3 chloride ions. Hope you were staying a step ahead of me there. Wait a minute, I'm not balanced. I added water to the left-hand side to make 3 hydroniums. To keep it balanced, I'm going to have to add 3 waters. Now that should be 6. And now I'll double check. 6 oxygens on the right-hand side, 3 oxygens plus 3 oxygens, 6 oxygens. Good. Now, what would I see when I carried out that reaction? I would start with a solid in the starting material, and when I'm done, I should have said this up in the earlier equation, when I'm done, there's no solid left. I end up with a homogeneous solution. Iron 3 hydroxide isn't soluble in water, but it was soluble in hydrochloric acid. Pretty cool, huh? All right, last step, net ionic equation. You're way ahead of me. I'm going to leave out the spectator ion. And what didn't change from reactants to products in the complete ionic equation? The only spectator ions we have this time are chloride ions. So we'll keep everything else when we write the net ionic equation. Iron 3 hydroxide solid plus 3 hydronium gives me 6 waters, and iron 3 plus aqueous. And at the level of the net ionic equation, what do we see happening? We see that the acid gives its proton to the base. The 3 hydroxides pick up 3 H pluses and make 3 water. And what's left from the 3 hydronium, when it lost the 3 H pluses, we were also left with 3 water. So that's how I get 6 waters altogether. Pretty cool, huh? All right, this was a long one, but we finished talking about acids and bases. When we come back, we will look at oxidation reduction or redox reactions.